Okay, we're at section 2112, spectrum of E&M waves. Let's go to the next slide. All electromagnetic waves travel in a vacuum with the speed of light c and transport energy and momentum. In 1887, Hertz successfully generated and detected the radio frequency electromagnetic waves predicted by Maxwell. Maxwell himself had recognized as electromagnetic waves both visible light and the infrared radiation discovered in 1800 by William Herschel. It is now known that other forms of electromagnetic waves exist that are distinguished by their frequencies and wavelengths. The different types of E&M waves are shown in this figure. The waveforms of visible light, for example, range from 0.4 millimeters to 0.7 millimeters, or 400 nanometers to 700 nanometers. I'm a little more used to nanometers. Or 4,000 angstroms to 7,000 angstroms. Because all electromagnetic waves travel through free space with a speed c, their frequency and wavelength are related by the important expression shown here, c equals f lambda. So the speed of light is equal to the frequency times the wavelength. Okay. The abbreviations given here are often used to designate short wavelengths and distance. 1 micrometer is equal to 10 to the 6 meters. 1 nanometer, which is the hundreds of nanometers are specified light waves. 1 nanometer is equal to 10 to the minus 9th meters. And 1 angstrom is equal to 10 to the minus 10th meters. Angstroms are used a lot in astronomy. Let's take a look at the different types of E&M radiation. Be aware that there is no sharp division between one kind of electromagnetic wave and the next. All forms of electromagnetic radiation are produced by accelerating charges. If you look at the bottom in the bold rectangle, radio waves are the result of charges accelerating through conducting wires. They are, of course, used in radio and television communication systems. Oops, oh. Let's go back here. Microwaves, short wavelength radio waves, have wavelengths ranging between about 1 millimeter and 30 centimeters and are generated by electronic devices. Their short wavelengths make them well suited for the radar systems used in aircraft navigation and for the study of atomic and molecular properties of matter. Microwave ovens are an interesting domestic application of these waves. It has been suggested that solar energy might be harnessed by beaming microwaves to Earth from a solar collector in space. Infrared waves, sometimes incorrectly called heat waves, produced by hot objects and molecules, have wavelengths ranging from about 1 millimeter to the longest wavelength of visible light, 7 times 10 to the minus 7 meters, 700 nanometers. They are readily absorbed by most materials. The infrared energy absorbed by a substance causes it to get warmer because the energy agitates the atoms of the object, increasing their vibrational or translational motion. The result is a rise in temperature. Infrared radiation has many practical and scientific applications, including physical therapy, infrared photography, and the study of vibration of atoms. Visible light, the most familiar form of electromagnetic waves, may be defined as part of the spectrum that is detected by the human eye. Light is produced by the rearrangement of electrons in atoms and molecules. The wavelengths of visible light are classified as colors ranging from violet with a wavelength around 4 times 10 to the 7 meters or 400 nanometers to red with a wavelength of around 7 times 10 to the minus 7 meters or 700 nanometers. The eye sensitivity is a function of wavelength and is greatest at a wavelength of about 500 nanometers, 5.6 times 10 to the 7 meters, which is yellow-green. Ultraviolet light. Ultraviolet light covers wavelengths ranging from about 400 nanometers down to 0.6 nanometers. The sun is an important source of ultraviolet light, which, by the way, is the main cause of suntans. Most of the ultraviolet light from the sun is absorbed by atoms in the upper atmosphere or stratosphere, which is fortunate because UV light in large quantities has harmful effects on humans. One important constituent of the stratosphere is ozone, produced from reactions of oxygen with ultraviolet radiation. The resulting ozone shield causes lethal high-energy ultraviolet radiation to warm the stratosphere. There is even divisions of ultraviolet. There's UVA, UVB, and UVC. You'll see those designations on some sunglasses as to which radiation they absorb. Okay, X-rays. X-rays are electromagnetic waves with wavelengths from about 10 nanometers down to 10 to the minus 4 nanometers. The most common source of X-rays is the acceleration of high-energy electrons bombarding a metal target. X-rays are used as a diagnostic tool in medicine and as a treatment for certain forms of cancer. Because X-rays easily penetrate and damage or destroy living tissues and organisms, care must be taken to avoid unnecessary exposure and overexposure. Gamma rays. Electromagnetic waves emitted by radioactive nuclei have wavelengths ranging from about 10 to the minus 10 meters to less than 1 to the minus 14 meters. They are highly penetrating and cause serious damage when absorbed by living tissues. Accordingly, those working near such radiation must be protected by garments containing heavily absorbing materials such as layers of lead. All right. Observations. When astronomers observe the same celestial objects using detectors sensitive to different regions of the electromagnetic spectrum, they see striking variations in the object's features. These images show the Crab Nebula made in 3 different wavelength ranges. The Crab Nebula is the remnant of a supernova explosion that was seen on Earth in about 1054 AD. So from left to right, these are observations of different parts of the electromagnetic spectrum shown in different features. They show different features of the Crab Nebula. So A is an X-ray image, B is the optical image of the Crab Nebula, C is the infrared image, and D is the radio image. This ends the spectrum of EM waves. And next we're going to discuss chapter 2113 briefly, the Doppler effect.